We are going to be looking at the September 2019 chemistry paper, question 8, which is a question on voltaic cells. But before I start with the question, I just want to point out that I will be doing this question using table 4b. So when you get your exam paper and you intend using table 4b, you need to draw a line through table 4a so that you do not use it by mistake. We are going to be looking at September 2019, question 8 of the chemistry paper, paper 2. This is a question on voltaic cells. So before I start with the actual question, I would like to look at table 4b. If you intend using table 4b, you must draw a line through table 4a so that you do not use it by mistake. So in table 4b, I know mine is very small, but I wanted this all to fit on the screen. When you look at the table, the arrow down the left-hand side indicates the increasing strength of the oxidizing agents. So these are your oxidizing agents. They are the substances that will be reduced. The arrow on the right-hand side going up is indicating increasing strength of the reducing agents. So these are the substances that will be oxidized. So for example, if lithium has to be oxidized, lithium is reacting to be oxidized. Lithium needs to be on the left-hand side, so we will swap this reaction around. Every time a half reaction is used as an oxidation half reaction, you need to swap the reaction around. Whatever is on the right-hand side goes to the left, and whatever is on the left-hand side will go to the right-hand side. When you are doing voltaic cells, as we are going to be doing in this lesson, you need to identify your two half reactions. The top half reaction will be the oxidation half reaction, and that is the half reaction that you will swap around. The bottom half reaction will be your reduction half reaction, and please remember to always use single arrows. When you do a question with electrolytic cells, these are cells that have an electric power supply, a DC power supply. Again, identify your two half reactions from the table. The bottom half reaction will be the oxidation half reaction, and this half reaction has to be swapped around. It is always the oxidation half reaction that has to be swapped around. So for electrolytic cells, which are not spontaneous, you swap the bottom half reaction around, and the top half reaction will then be your reduction half reaction. Again, use single arrows. I must stress that this is for the table 4b. So if we go back to the table, our strong reducing agents are these substances up at the top. So they are easily oxidized. They will easily lose electrons. The bottom right, these are weak reducing agents. So they don't like to be oxidized. They don't want to lose electrons. On the left-hand side, the arrow is coming down, indicating the strength of the oxidizing agents. So your very strong oxidizing agents are down here. They are easily reduced and like to take up electrons. Your weak oxidizing agents are up here, as I've indicated on the table. They are weakly reduced. They do not want to take up electrons. So now I'm going to go across to our question that we're going to do. September 2019, question 8. I've made quite a few notes on this sheet. So question 8, the diagram below shows a galvanic cell. A galvanic cell and a voltaic cell are the same type of cell. It has two names. It is set up under standard conditions. I will speak about what those are just now. In a voltaic cell, chemical energy is converted to electrical energy. When they ask you for the energy conversion, please write a sentence. Don't say chemical E, arrow, electrical E. Write a full sentence. Now, when using the table 4b for a voltaic cell, I'm going to repeat. The top half reaction must swap to become the oxidation half reaction, and the bottom half reaction will be the reduction half reaction. Always use single arrows. Before you begin your question, you must always identify your two half reactions, because they will help you so much with answering the questions. The two half reactions for this Voltaic cell, let's first look at the sketch. We have bromine liquid and bromide ions in half cell A. In half cell B, we have iron 3+ ions in solution and an iron electrode. On the left-hand side in cell A, I have a platinum electrode. Now, the reason for having a platinum electrode is because we do not have a metal reacting here that could serve as an electrode. Bromine is a liquid, and bromide ions are ions in solution. Please remember, ions are always in solution. You will always have aqueous written behind your ions. As I said, bromine is a liquid, so in that case, they will always use platinum or graphite as an electrode. We'll speak more about that just now. I'm going to go to the table and identify the two half reactions. So when we do that, we see that iron is higher up than the bromine. So please make sure that you choose the correct iron half reaction, because there's iron 3+ taking up an electron to form iron 2+. There's iron 2+ taking up 2 electrons to form iron, and iron 3+ taking up 3 electrons to form iron. So this is the one that I need. It was iron 3+ taking up 3 electrons to form iron. But this half reaction was higher up on the table, so it becomes my oxidation half reaction. The bromine half reaction was quite a lot lower down, so this one is my reduction. Take note, I swapped the top one, whatever was on the right, I put on the left, whatever was on the left, I put on the right, and I used single arrows. Oxidation always occurs at the anode, reduction always occurs at the cathode. So we can have a little rhyme, anox, anode, oxidation, red cat, reduction at the cathode. So if oxidation is my iron half reaction, this half cell B will be my anode, and half cell A, where reduction takes place, will be the cathode. Now, electrons leave the anode because that's where oxidation takes place. Electrons are given off. They travel through the circuit. This is an ammeter that will measure microamperes. And the electrons travel through the cathode onto the platinum electrode where the reduction half reaction will take place. If they ask you for a possible electrolyte for this solution, the bromide ions will need positive ions to attach to them because all solutions will always be neutral. Always choose an ion from group 1. We'll need a positive ion, so choose sodium ions or lithium ions or potassium ions, because all group 1 salts are soluble. So then you don't have to learn your solubility rules from grade 10. On this side, where we have iron 3+, Fe3+ ions, you don't have to learn solubility rules. Just remember, all nitrates are soluble. I cannot make subscripts with this program. So that's a subscript 3 and a subscript 3. So a possible electrolyte on this side will be FeNO3, where we have 3 nitrates, because each nitrate has a oxidation number of -1 or charge of -1. So nitrates, all of them are soluble. So you will always be safe and know that your electrolyte is soluble. This is our salt bridge, which will contain an ionic substance. So I'm going to say, for example, we have potassium iodide in the salt bridge. Potassium iodide will have positive potassium ions and negative iodide ions. So you must always have an ionic solution in your salt bridge. So I'm going to start with the questions now. Write down 2 functions of the salt bridge. So in my notes down here, I have the functions of the salt bridge. This can be a 3-mark question. The salt bridge is there to complete the circuit, to provide a pathway for ions to flow, and the reason for that conducts the current through the solutions, and also it keeps the 2 half cells neutral. So if we look at our 2 half reactions, which I got from table 4B. The iron metal over here in half cell B, each iron metal atom gives off 3 electrons to make more ions in solution. So this iron Fe concentration, the iron concentration, will increase. And the iron metal will start to look like it's corroded. It will lose mass because the iron metal atoms are reacting. So whatever negative ions I had in here to neutralize these positive ions, their concentration will stay the same. But I keep forming more Fe3 plus ions in solution. So the iodide ions from the salt bridge will move in here to cancel out the extra positive charge that is created by the formation of more Fe3 plus ions. That I see from the half reaction. So that is a reason why we always write our half reactions. We can see so much from the half reactions. So the anions, negative ions are anions. The anions from the salt bridge move into the anode half cell. Now what happens at the cathode? We need to look at our half reaction. The neutral bromine liquid, each molecule will break up into 2 separate atoms. Each atom takes up an electron to form 2 bromide ions. So this solution, the bromide ion concentration will increase. So whatever positive ions we had here, that concentration will remain constant. So we're forming more and more negative ions. So the potassium ions from the salt bridge, which are positive, they will move in here to neutralize the extra bromide ions that form according to this half reaction. So the cations, the positive ions, move into the cathode side from the salt bridge. So let's just recap that. From the salt bridge, the anions move to the anode side, the cations move to the cathode side. So this salt bridge, as you can see, is completing the circuit. If you had to lift it out, it's just a U-shaped glass tube with a salt solution in, potassium iodide, with cotton wool shoved in the ends. So as soon as you lift this out, your ammeter reading goes to 0 because you've made a break in the circuit. So it completes the circuit, provides a pathway for ions to flow, and it helps to maintain electrical neutrality in your solutions. So as I said, electrons will leave the anode, flow through the ammeter, and come this side through the cathode. So in our external circuit, we have electrons flowing from the one electrode through the wire, through the device to the other electrode. Electrons flow there, ions flow in the solutions and the salt bridge. You need to know what conducts the current and in which part of the circuit. So if we look at our questions, we've now done 8.1. Then which half cell A or B contains the cathode? I got that answer from my 2 half reactions. Always write your 2 half reactions. They were never asked in this question, but by now you can see how many times I've used them. So from the 2 half reactions, swapping the top one, I can see that this one is reduction. So this happens at the cathode. So half cell A is the cathode. So there's your answer there. Why is half cell A the cathode? Because reduction happens at the cathode. Red cat. Reduction is the half reaction that is lower down on the table of the 2 half reactions. Then 8.3, write down the balanced equation for the overall or net cell reaction. So again, I couldn't do that with confidence if I hadn't written the 2 half reactions. Electrons always need to balance. So I would multiply this half reaction with 2 and this half reaction with 3. So you can do this in pencil in your exam, but your final answer must be in pen. So I'm just balancing my electrons quickly. Okay, so everything that is on the left-hand side, the 2 iron metal atoms react with 3 bromine liquid molecules. You don't write the electrons in. It forms 2 iron 3+ ions and 6 bromide ions. So these are on the right, they go on the right. Those two are on the left-hand side of their respective arrows, so they go on the left. A nice way to check that you haven't made any careless mistakes is to check that the total charges on the left, in this case it's 0, equal the total charges on the right-hand side. 2 times +3 is +6, and 6 times -1 is -6. So they balance, so it's unlikely that there are any careless mistakes there. 8.4. Calculate the initial EMF of the cell. If there was a voltmeter here, what would that voltmeter read? You go to table 4B and you write down E cell. You copy this from the data sheet. It's cathode minus anode, or reduction minus oxidation. This sign means that the values were determined under standard conditions. So your bromine is reduction, the bottom one, you put that down first, minus the iron half cell potential. So the negative and the negative becomes a positive. Your answer is 1,13 volts, which it must be a positive value if it's a voltaic cell, because voltaic cells are spontaneous. I will do the cell notation later. It wasn't asked in this question. Then the standard conditions that I was referring to are these down here with a purple highlight. The standard conditions for voltaic cells: temperatures must be 298 Kelvin or 25 degrees Celsius. Your solutions must all have concentrations of 1 mole per decimeter cubed, and should gases be present, there are no gases in my example here, the gases must be under standard pressure. This standard pressure is on your data sheet. The temperature they're referring to here is not the standard temperature on your data sheet. That standard temperature on your data sheet is 273 Kelvin, which is 0 degrees Celsius. The standard temperature for these voltaic cells is 298 Kelvin, which is 25 degrees Celsius. So now I said that in this half cell, we have a platinum electrode because there is no metal that can act as an electrode, or no solid that can conduct that acts as an electrode, unlike half cell B, where we have an iron electrode, where iron is your reactant. If your electrodes are not metal reactants or products, you're going to have to use graphite or platinum. And the reason they use platinum and graphite is here with a blue highlighter. They are used as electrodes when there isn't a solid reacting electrode or electrode as a product. Platinum and graphite are good choices as they are solids. They are inert, meaning they do not react with the reacting substances, and they are good conductors of electricity. They sometimes ask, why do they use graphite, or which is a form of carbon, or platinum as electrodes? Now, the last thing I still need to do here is write the cell notation for the cell, which was not asked. The cell notation has a few rules. There are a few rules. Here they are with a yellow highlight. You always put oxidation first, then the double line to represent the salt bridge, and then the reduction. Your electrodes must be first and last in the cell notation. We use a line between different phases and a comma between same phase. Okay, so you read your half reactions from left to right. So again, I'm using half reactions that were not asked, but they've come in handy so many times. So the cell notation for this cell, you do the oxidation first. I'm going to do it with phases. So the iron comes first because it's on the left-hand side. Oxidation is on the left of the double line, then reduction. I'm going to do this one first. The iron metal forms iron ions. So that goes from a solid to a solution with ions. So I need a line because it's a phase change from solid to ions in solution. Now I'm done with this one. I can see from the half reaction I've got what I need there. We never put electrons in. So we do the double line now to show that we're going on to the reduction part. Don't use balancing numbers either. No electrons and no balancing numbers. And also you do not put water in when it is pure water like H2O liquid. Now for reduction, we read from left to right again. So it's Br2 liquid, Br2 liquid, forming bromide ions in solution. So that's a phase change. Br minus ions in solution. And what is the electrode here? There's no bromine or bromide electrode, so it's the platinum electrode. So it's PT solid. So my electrodes are first and last. So that is the cell notation for the cell. Then the last question we need to look at is 8.5. The bromine bromide half cell is now replaced with the iodine iodide half cell at standard conditions. Will the initial ammeter reading be higher or lower when the iodine iodide half cell is used? Explain your answer by referring to the relative strengths of the oxidizing agents involved. Bromine is a stronger oxidizing agent than iodine. Bromine is lower down on your table on the left-hand side, the table 4B that I was referring to earlier on. Bromine is a stronger oxidizing agent than iodine. So if you replace the bromine with iodine, you're going to have a lower cell potential than when we use the bromine.